let's say, a pretty long wire. Let's say the current is coming down and then going to the right. So let's say you're told that the wire is very long. You don't necessarily be needing to give you the length of that wire. All you need to know, oh, okay, the wire is very, very long. So now you could be asked, what is the total B field, let's say 40 centimeters and 20 centimeters. So at this point, what's the B field, 40 centimeters and 20 centimeters this way? You see, so at this point. And you could even be told 40 centimeters and 20 centimeters up like this. So let's just choose 3 points. 40, 20 this way. Let's call this point P. Let's call this point P prime. Find the total B field here. Find the total B field here. Find the total B field somewhere above the page here. It's almost like this. You see? So P double prime, somewhere over here, you see, in the Z plane. So how would you do something like that? So find the total B field at P prime, P double prime out of the page. Assume the wires are very long. So this is kind of a geometry type problem. Okay, so what equation do we use? The fact that we are outside of the wire and the fact that the wire is long, that means this equation applies. B is mu0 I over 2 pi r. Okay, so that one applies. So now just a matter of keeping track. Let's call this segment of the wire, wire 2. And then let's call this segment of the wire 1. Okay, so what's the B field created by this? What is the direction of the B field created by this at P? Okay, so put your thumb in the direction of the current flow. Then curl your fingers, you see? So go like that. And you gotta curl your fingers around. Oh man, it's my hand. If your hand is not hurting when you do this, then you don't get an A on the test. Right? So then it comes out of the page. So B here, we could say B1 is in the Z direction. If this is X, imagine X, Y, Z. So B1 is out of the page. Right? And then now B2 is what? Like that, current. Okay, that one's less painful. You see, out of the page. So B2 is also out of the page. Okay, then it's just a matter of adding the two. So at P, B total is going to be mu0 over 2 pi I1 over R1 plus I2 over R2. Okay. So the mu0 over the 2 pi is constant, so we can just pull that out. So then this one is, of course, going to give you 2 times 10 to the minus 7. I1 is equal to, okay, well, the current is the same. I'm assuming it's a one current that's flowing through both. So I1 is 1.2 amps, let's say. I2 is also 1.2. Right, so then it's just going to be, well, actually the current is the same, so we can also factor that out, and it'll just be 1.2. Then it'll be 1 over R1. So then it's just the R1 is going to be 0.4, right? Plus 1 over R2, 0.2. Okay, that one wasn't too bad. So over there, the only problem that you could have maybe made is maybe thought that, oh, you should subtract them or something, you know. So you just have to do the right-hand rule to see, okay, they're actually in the same direction. So then, let's see. 1 divided by 0.4 plus 1 divided by 0.2 times 2 times 1.2. 18 times 10 to the minus 7. 1.8 microtesla. Okay, cool. Now, how about point P prime? At P prime, what's the field here? Now, you might think, oh, wow, this is crazy. I have to worry about that angle, you know. It's kind of outside of the bounds of the wire. But remember, this wire is assumed to be very, 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 very long. So you could still use the equation. What's the direction of the field created here? It's still this way, and it's still out of the board. You see? So it actually doesn't change. It's tricky. The field here, due to B1 is still out of the page. See, haha, scared you. When you probably first saw that, when you first see that, most students will go, they'll panic. What? How do I handle that? You know, and then you realize, oh, it's actually the same thing as the B field here. It doesn't matter because this is a long wire. I don't need to worry about its dimensions. As long as I'm 40 centimeters away from the wire, this distance is what matters. You see, imagine continuing this wire as long as I'm 40 centimeters away. That's what matters. You see that? So the B total. Oh, now how about this guy's B field? Okay, now that one. Oh, okay, now that one is going to be like this into the board. You see, over here, it was out of the board. Oh, so that one changes, you see. Over here, the B field created by this guy was out of the board. And then over here, it is into the board. Ooh, okay. So then B total is going to be B1 minus B2. Now they're fighting against each other. So mu 0 I over 2 pi, 1 over R1 minus 1 over R2. Oh, actually, the one into the board will win because it's only 20 centimeters, you see. Yeah. So it's going to be, this is going to be 2 times 10 to the minus 7, 1.2 amps, 1 over 0.4 minus 1 over 0.2. So out of the board, let's say out of the board means positive, which it usually does mean, you know, out of the board. So then this is going to come out negative. One divided by 2 times 1.2 times 2. Negative 6 times 10 to the minus 7. Negative 0.6 microteslas. So it's into the board. Yeah, here it's into the board. Okay, how about the one that's coming out this way? Okay, here we have to be a little bit more careful probably. Okay, so this one, the B2 is going to be like this. And you see, so if it's out of the board right there, the B field created by the second wire is going down. You see that? Remember, it's over here. So it's like this, boom, like that. It's going down. So B2 is this way. B2, its magnitude will be the same as what we had here. It's in the negative y direction. So how should we write that? It's going to be mu0 I over 2 pi r in the negative j direction, right? This one, in the negative y direction. How about this one? Hold on. Let's see here. I'm trying to visualize that now. If the point is here, the field created by this guy will wrap around it like that. Ooh, that one is a tricky one. If it's here, then the field will go like that. It will wrap around. Oh, okay. So you see that one's a hard one now. This one here, it's gonna make a circle around the wire. So when you get there, it's gonna be like this at an angle. You see, because it's going around like that. So over there, it's this way. You guys see that? Man, it's hard. Yeah, it's like this. It's like this, like that. I don't know if you can't capture it that well. You guys see that? Oh, someone said no clue, Matthew. Now you don't see it, huh? So you have to kind of visualize as like distance from here to here, right? And then a circle, making a circle around there. You see, so you're at over here. So it's going like this, perpendicular to that. So which direction is it going to be in? It's going to be in the negative x direction and the z direction. And then the field due to this guy, this wire, is going to come like this. So over here, it's going to be in the negative y direction. Oh, okay. So then what's the magnitude of that D field going to be? Mu0 I over 2 pi r. That's the magnitude. So then what's the r? 2 times 7 1.2 over, what's that distance? So if it's 40 this way, 20 that way, so what's that distance here, from here to here? 40, 20. That distance would be 40, 20. It's kind of like this is one way of drawing it, probably just visualizing it like this, but this 20 is really out of the page, you see. So then 40, 20, and then this is the wire. Yeah, that's probably one way we could watch. It's almost like we're watching it from the bottom and drawing what the picture would look like from the bottom. We would see a current coming toward us, then we would see 40, 20, and then the D field would be like this, you see. Yeah, that's a good way of drawing it in the plane of the paper. So then that distance would be what? This is centimeters. 40 squared plus 20 squared square root. Well, let's just write it as 40 squared 1600 plus 400, right? Yeah, 400. So square root of 2000, let's just say 2000. Right? So then that's going to be over square root of 2000. But now, let's break that into components. So if this is the B field, what's this going to be? So this component coming this way is going to be the BZ. And then this component is the one that's going to be coming. So if it looks like this. So this one is going to be BZ, and then this component is going to be BX. Let's see, so this is going to be BX. So it doesn't actually have a BY. This guy, the other wire, has only a BY. You see? So then how do I get the BZ and the BX? Well, I can say this is theta. Then this would be theta. If this is theta, this is theta. This is 90 minus theta, and then this is theta. Right? Theta, theta, 90 minus theta, theta. So then I could say BZ is going to be this times cosine theta. Right? So BZ is this magnitude. So cosine theta k hat, right? And then BX is going to be in the negative direction. Negative this magnitude times sine of theta, right? That's I hat. See, it's in the negative. This one was a harder one, quite a bit harder than those. Those are tricky too, but it's limited trickiness. This is a lot harder. You have to really visualize 3D.
Professor, quick question.
Yeah.
Why didn't we say that B2 was negative J hat?
That one was because this guy is going this way, and then it creates a B field this way, and it's opposite to the y direction.
Oh, for that. Oh, okay. I thought that was for P double prime. That's why.
Yeah, that is P double prime. Yep.
Wait, P double prime is where?
Is out of the board right there.
Okay. Oh, above
you see somewhere here.
line.
You see that? Like that.
Oh, okay. Got it.
Yeah. So it solely creates a B field in the y direction.
Okay. Yeah. For a minute, I thought P double prime was above just P. That's why.
Oh, above P?
Yeah.
Yeah, then that would have been, because I made it 40 and 20.
Got it.
Yeah, you could have made it another one here above that, Oh, but then that would have been harder because if it's, then that's harder because now this one creates a field, also has a weird direction. You see, it would go like that.
Right.
So this one would be harder problem than above this. Because now both of them would have an angle. You see?
Got it.
Yeah, this is at least one step easier because this one only has a B field in the y direction. Yeah. So let's see here. Then you're going to do cosine theta is just going to be 40 over square root of, So you go this one, 40 over square root of 2000 k hat minus the sine of theta is going to be 20 over square root of 2000 I hat. And then all of this, okay, let's see what all of that comes out. So 2.4 divided by 2000 to 2.4 over 2000 square root. But remember, this was centimeters. So then I have to multiply this by 100. Okay, so then that gets rid of this times 10 to the minus 7. Well, you know what? It's just 2.4 divided by 2,000 square root times 100. Yeah, we could have just written it this way. So we just say B is equal to 5.3665 times 10 to the minus 7. And then this is just 40 over 2,000 square root. This one you don't have to convert to meters because they're both centimeters, so it's unitless. Okay, minus, and this is half of that. Then we could distribute this in, so call this 0.53655 microtesla, right? And then just distribute that in. So 0.53665 times 0.894427. Okay, so then my final answer is going to be B total. This is going to be the Z component. So 0.47999, pretty much 0.48, huh? K hat. In the X direction, it's going to be 0.53665 times 0.447214. So then minus 0.23999. You know, I'm just going to make it easier. This is 0.48. This is 0.24 I hat. Okay, now let's do the J hat, the other wire. Then that's just 2 times 10 to the minus 7 and 1.2 over, and you are 20 centimeters above that wire, so it's just the distance is 0.2. That's it. That one's very easy. 0.2, negative J hat. So then that's going to be 2 times 1.2 divided by 0.2. 12 times 10 to the minus 7, negative J hat. So 1.2 microteslas negative J hat. See? So then that's the magnetic field created by the other wire, wire 2. Okay, then we can bring that and add it to this guy. So the total magnetic field is 0.48 K hat, negative 0.24 I hat, and then negative 1.2 J hat. There you have it, microteslas. So none of the components added up. You just have a Z, a Y, and an X. Now if I want to find the total magnitude of the B field, you do this squared plus this squared plus this squared, square root. So of course it's harder because we're dealing with a true three-dimensional vector. So 0.48 squared plus 0.24 squared plus 1.2 squared square root 1.3145 microtesla. That's the field strength at that double prime point. That one was challenging, huh? Yep, that one was challenging. Where would be another point that would maybe not be as challenging? It would be a quick one. Let's see. This is not too challenging, it's quick. This is not too bad once you know how to do it. How about something like this on top of this wire here? Is that challenging or not that easy? In other words, you could do the top of this wire 20 centimeters above this, or even at the corner 20 centimeters above. Would that be easy? Actually, what would it be? The B field right at the corner 20 centimeters above. You could do it in your head now. No calculation needed. Hint, hint. Oh, actually, no, hold on. No, you do need a count. Oh, no, it's not that quick. Dang it. It is easy, but not that. Let's see. Let's see here. If it's here. Oh, okay. Here is a little bit more work. If it's somewhere here, random, above that wire, it is more work because the field of this, you see, the field of this will be at an angle. Yeah, that is a little bit. Yeah, that is a little bit more work. Yeah. But right at the corner is quick. Right at the corner is another very quick one. It's similar to this, right at the corner. Okay, so we can call that P triple prime. 20 centimeters above the corner right here. Right here. You see, that's a quick one. The field of the wire 2 is going to be what? Down, negative J direction. The field of wire 1 is going to be like this, right? And then curl around. So the field of this guy will come around, and then over at the corner, it'll be this to the left. You see? And then the field of wire 2 will be down. So you don't have to break them into components. You see? So that's a more quicker one. P double prime is the longest one here. So then the total B field will be what? 2 times 10 to the minus 7 times 1.2. So it's got a negative J component, right? This one, due to this guy. So it's 1 over 0.2 negative J. And then how about this guy? It's got a magnetic field going to the left. You see, so it's got a negative X component. That's it. They're both equal because it's 20 centimeters. It's 20 centimeters from this guy above, and then it's also 20 centimeters from this guy above. And they have the same current, so there's nothing else. That's it. So it's just literally 2 times 1.2 divided by 0.2. So it's going to be B is going to be 1.2 microtesla negative I hat negative J hat. Yeah, so it's going to be this way and then this way. And if you want to do the magnitude, it'll just be 1.2 square root of 2 microtesla. That's the magnitude. Yeah, so that's a quick one. P triple prime. Okay, right there. It has this way and it's got that way. Negative X direction. Okay, good guys. So that one was an easier one, but of course the two easiest were probably this one, and then that one is next. But then this one over here above this wire was a harder one. Oh, the hardest will be if it's somewhere above there. Then it's even more complex.